Click the bell icon to get latest videos from Ekeeda.
Hello friends, so in this video we are going to study the interference in thin film due to reflected light. We are actually going to find out the expressions that will help us find the fringe width due to the interference pattern that is developed in a interference film. So, in order to study the interference in thin film, first of all, let us study the ray diagram. Here is the ray diagram. So, this is the film of thickness T. You are having the incident light that is represented by the ray AB. At this particular point, there is going to be partial transmission and partial reflection. So this is going to be the reflected ray, BC is going to be the reflected ray, and BD is going to be the transmitted ray. BD is of course the refracted ray also. At the point D, once again there is going to be partial transmission as well as partial reflection. Remember, we are dealing over here interference due to division of amplitude. Now when the ray reaches at the point D, once again there is going to be a partial reflection and the partial transmission. When the reflected ray reaches the point E, once again there is going to be partial transmission and partial reflection. And the same thing happens out over here, that is at the point G. So this one can say DF and GH are the two rays which are transmitted, and BC and EF are the two rays which are actually reflected. So when we are considering the interference due to the reflected light, we are going to focus only on this particular part. So first of all, let us try to find out what is the path difference between the ray BC and between the ray EF. Now this ray EF has actually traversed this additional distance, and hence the path difference delta is going to be BD plus DE minus BM minus BM, and this is going to be your M. This is incomplete. This is the distance that is traveled inside the medium, and therefore I need to multiply this by the refractive index, that is mu. Let us try to find out what is BM. For BM, from geometry, this is going to be equal to I. Let us find this as expression 1. Now your sine I is going to be equal to opposite side, which is going to be equal to BM divided by the hypotenuse, which is going to be equal to your B. Similarly, if at all I am applying the Snell's law at the point B, you're going to be equal to sine I upon sine R is going to be equal to mu. Therefore, from these two expressions, you are having your BM is equal to BE into sine R, but you can very well write your sine R as BM will be equal to BE into your sine I, and from here your BM is going to be equal to BE into mu into sine of R. So for the BM out over here, I can substitute it very well as this is going to be equal to mu into twice of BD. I am writing twice of BD because this distance and this distance is same, minus of BM, which is going to be equal to mu into BE into sine of R. Let us now try to find out what is the alternate expression for your BE, and for doing that, let us consider this triangle, that is B, L and D. So from this particular triangle, so one can write in triangle B, L and D, right? We have your sine of R is going to be equal to BL upon the hypotenuse, which is going to be equal to BD. Or you can write 2 into sine of R into BD is equal to 2 into BL. L is the midpoint of B and E, and therefore your twice of BL is nothing but your BE. So let us write this as expression 2, and you can very well write, so I'm continuing from this expression out over here, that your BE is going to be equal to twice into sine R into BD. So let us say this is your expression 3. Now I substitute this expression out over here. So we have derived two important expressions. First of all, delta is equal to mu into 2 into BD minus of mu into BE into sine R, and BE is equal to 2 into sine R into BD. Let us substitute expression 3 in 2, and therefore your path difference delta is going to be equal to 2 mu into BD minus of 2 mu into BD sine of R into sine of R. Hence, your delta is going to be equal to 2 mu into BD into 1 minus of sine square R. Now, since this is sine square R, I can very well write this as 2 into mu into BD into cos R into cos R. What I mean is, it is nothing but cos square R. Can we simplify this further? Yes, we can do that. Let us look at this diagram once again. So we have cos of R from here. If you want to write down cos R in this particular triangle, your cos R is going to be equal to your adjacent side, which is going to be your LD. But what is LD? LD is nothing but the thickness divided by the hypotenuse, that is nothing but your BD. So your thickness is going to be a multiplication of BD multiplied by cos R. So we substitute this in the final expression. So we have cos of R is equal to T divided by BD, and this is from geometry, or your T is going to be anything of BD into cos of R, which is going to be your expression 4. So I'm going to substitute this expression in the above expression, which let us say I'm labeling it as equation, which we are labeling it as equation 3. So your delta is going to be equal to 2 mu into BD into cos square R, which now can be substituted as 2 mu T into cos of R. And that is the final expression for your path difference, which is going to be equal to 2 mu T into cos of R, where mu is going to be the refractive index of the medium, T is going to be the thickness of your thin film, and R is nothing but the angle of refraction. And let us label this particular expression as expression number 5. In this, we have forgotten one thing. If we go back to the figure, you will be able to see that the reflected rays, all of them are getting reflected from the denser medium. Let us have the look at the figure. So here is the figure. So you see that this rays BC and EF, for which we are deriving the interference equation, these are the reflected rays, and they are getting reflected from below is the denser medium, and hence from Stokes' law you have to add an additional parameter of and hence from Stokes' law you have to add an additional parameter of lambda by 2. Hence your delta is going to be equal to 2 mu t into cos of r and plus lambda by 2. So this is your final expression for the path difference. This path difference, suppose now we are finding out the condition for constructive and destructive. We are now trying to find out the conditions for constructive and destructive interference. So we know that for constructive interference, the path difference is going to be an integral multiple of lambda. So from this expressions, which is going to be equal to, let us say, 6, and this is going to be equal to 7, I'm going to equate these two expressions and let us see what we get. So this is going to be equal to 2 mu t into cos of r plus lambda by 2 is equal to n into lambda, which simplifies to 2 mu t into cos of r is equal to n lambda minus of lambda by 2, which is going to be equal to 2 n minus 1 into lambda by 2. Thus 2 mu t into cos of r is equal to 2n minus of 1 lambda by 2. Thus 2 mu t into cos of r is equal to 2n minus 1 lambda by 2. This is the expression for the constructive interference. Similarly, let us try to find out the expression for the destructive interference. We know that for the destructive interference, your delta is going to be equal to 2n plus or minus 1 lambda by 2. So when we see that, wherein your n is going to be equal to 0, 1, 2, etc. So now what we do is, I once again equate your expression 9 and your expression 6, and let us see what we get. So this is going to be equal to 2 mu t into cos of r plus lambda by 2 is equal to 2n plus 1 into lambda by 2. And this, when I'm simplifying this, it is going to be equal to 2n. Therefore, that is going to be equal to n lambda, and this is going to be equal to lambda by 2, and this is going to be equal to 2 mu t into cos of r plus lambda by 2. So this lambda by 2, this lambda by 2 is going to get cancelled, and what I have from this expression is nothing but 2 into mu t into cos of r is equal to n lambda. So your condition, which is, let us say, the equation number 10. So this is the expression for the destructive interference, for interference in a thin film due to reflected light. Sincere thanks, students, for watching this particular video. Stay tuned to Ekeeda and do subscribe to Ekeeda. Thanks a lot.